Thank you for introduction. Good morning, good afternoon, good evening to all of you. I thank the organizers for giving me chance to present my research work. Today I am going to talk about our recent work on the 9-carbon breakup. Today I will discuss 4-body description of 9-carbon breakup. I am Jagjit Singh, and presently I am affiliated with RCNP as a concurrent researcher and a visiting researcher with Akal University. And today's seminar is based on our recent work, which is based on this archive preprint. And this work has been done in collaboration with Professor Ogata, Dr. Matsumoto, and Dr. Fukui. Okay, now I will explain the motivation for this study. 9-carbon is a proton-rich weakly bound nucleus with the large N by Z ratio, and it is bound by 1.4 MeV with respect to 3-body threshold. So one can see on the right side the schematic level diagram based on the data adopted from NNDC. In 9-carbon, the 3-body threshold is just 1.4 MeV, and all excited states of 9-carbon are in continuum. There also exists 2-body threshold, that is 8 boron plus proton threshold just below this 3-body threshold by 0.137 MeV, this difference. So in order to accurately reproducing these threshold energies and low-lying excited states, the 3-body model description for 9-carbon is desirable, but so far no such theoretical studies have been reported. And this 3-body structure model can be implemented in CDCC to describe the breakup processes of 9-carbon, which is in the sense essential to extract the astrophysical S factor from the experimental data in future. So the main aim or the main purpose of this study is to describe the ground and continuum states of 9-carbon by a 3-body model and to show how breakup reaction observables reflect these structures. The another advantage of this aim, which can be used in future, is like this. The related capture reaction to this nucleus, that is this capture reaction, have been intensively studied in past, both experimentally as well as theoretically with an astrophysical interest. So one can see from the figure on extreme right. So here, in past, all these theoretical studies and experimental studies have determined astrophysical factors. So one can see there is a significant discrepancy in the previous measurements for the determined astrophysical S factor. All these studies are reported different astrophysical factors, this discrepancy has triggered off new experimental studies on 9-carbon breakup. The preliminary reports on these experiments have been reported in these proceedings, and the figure is adopted from this reference by the co-authors of this study or collaborators of this study. So in order to support the upcoming experimental studies in which they aim to measure the 1 proton and 2 proton removal cross sections. So for such upcoming studies, it is important to describe 9-carbon as a 3-body system to evaluate the 2 proton removal cross sections. So this can be the motivation for us to describe 9-carbon as a 3-body system. Okay, so in order to To study the breakup of 9 carbon on a target, we use pool of frameworks. So in this whole story, the 9 carbon is our projectile and lead is target. To study the structure of 9 carbon, we make use of Gaussian expansion method for studying the ground and breakup states of 9 carbon. So for detailed insights of the continuum, that is looking for resonances in the continuum, we make use of the complex scaling method. Once the structure of projectile is fixed, we make use of these 3-body structure in the 4-body version of continuum discretized coupled channel method to study the breakup reactions of 9 carbon. Okay, now I will briefly introduce these frameworks one by one. The ground and discretized breakup states of 9 carbon are built within the framework of Gaussian expansion method by using Gaussian basis function. These ground and discretized breakup states are obtained by diagonalizing the 3-body Hamiltonian, which consists of various terms. The first 2 terms are the kinetic energy terms associated with the Jacobi coordinates. The next 2 terms are the interaction between the core and proton, for which we have adopted the central Wood section plus spin orbit Wood section plus the Coulomb interaction adopted from this reference. For proton-proton interaction, we make use of Coulomb plus Minnesota interaction. And we have the 3-body interaction, which is taken as the product of Gaussian functions for the 2 Jacobi coordinates. In Gaussian expansion method, the eigenstates are the solutions of 3-body Hamiltonian expanded in terms of Gaussian basis function. And all the 3 channels corresponding to different Jacobi coordinates are taken into account. And the Gaussian function consists of the spin part coupled to total spin S, the angular part coupled to total angular momentum lambda. The small lambda and L are the angular momentums associated with the Jacobi coordinates. These are the radial Gaussian functions with range parameters. And this is the summation over the number of basis function. So with all these ingredients for Gaussian expansion method, we obtain the ground and discretized breakup states. Now, in order to investigate the continuum of 9 carbon, we employ complex scaling method. So complex scaling method is a powerful method to study the many body resonances. In this method, the radial part of each Jacobi coordinate is transformed using these transformations with the scaling angle theta. So once we have the scaled Hamiltonian, the diagonalization of that complex scaled Hamiltonian leads to the eigenstates with complex eigenenergies. Okay, in red box, I have shown the schematic picture of non-scaled Hamiltonian, where we have a bound state and the continuum states on real with real energy. So once we scale our Hamiltonian by using the transformations based on scaling angle, we have the eigen energies, which are complex energies. So one can identify the resonances by plotting the eigen energy values in complex energy plane. Basically, in complex scaling method, a resonance is identified as an eigenstate on the complex energy plane isolated from the non-resonant continuum states. So this line shows the non-resonant continuum. Similarly, when we are describing three-body system, the three-body resonance is separated out from the non-resonant continuum. But if we have a resonance in subsystem, that is two-body subsystem, we can have a line parallel to this three-body non-resonant continuum, which can be identified as a one one valence particle sitting in the resonant state of two-body subsystem plus the third particle. Here it is the example of 6 helium actually. The third particle sitting in the non-resonant continuum. I can explain this in detail when I will show the results of 9-carbon continuum. So these resonant states are well isolated from the much dense continuum states. The real and imaginary parts of the eigenenergy represents the resonance energy and the half of the decay width, respectively. So with this, we can fix the continuum of our system. So once we have the structure information, we plug this structure information in the reaction model, for which we have used the well-established quantum mechanical reaction model, which take into account the Coulomb and nuclear breakup processes at equal footing. So the total, I will briefly introduce the formulation of 4-body CDCC. The total wave function of the system, that is projectile 9-carbon plus target reaction, is obtained by solving this equation, and where R is the radial coordinate between target and center of mass of the 9-carbon system, and Z is the Jacobi coordinates of the projectile. So this is the kinetic energy associated with the R coordinate. H is the internal Hamiltonian of 9-carbon. VPT is the interaction between proton and target. VCT is the interaction between core and target. And we solve this equation where the CDCC wave function is expanded by the eigenstates of 9-carbon, and we use pseudostate method to discretize the continuum in order to plug the proton target and core target potential. We make use of the distorting nucleus and nucleus potential, which are evaluated by the microscopic folding model. For nucleon potential, we make use of Melbourne G matrix interaction, and for the 7 beryllium and lead target, the Hartree-Fock wave functions based on the Guggenheim DIS interaction are adopted. So in CDCC, we solve coupled channel equation considering the coupling between discretized states, which leads to the transition matrix elements from where the breakup cross sections can be calculated. So as this is a discretized method, obtained cross sections are discretized in eigenenergies. So we adopted a established method developed by Matsumoto-san and group, to smooth our discretized eigenenergies, which is based on combination of CDCC and complex scaling method. For details, one can refer to this reference for more technical details, I would say. So with all these pool of frameworks, now we are ready to set up our calculations for the 9 carbon. Okay, so when we study a 3-body system, the spectrum of 2-body subsystem plays an important role. So for 9 carbon, the 2-body subsystem is 8 boron, which consists of proton and 7 beryllium core. In our study, for simplicity, we consider the 7 beryllium core to be inert and spinless. Of course, this is quite simple approximation. This is just to make our life easy. And 8 boron is known to be weakly bound system with valence neutron sitting in p3 half orbit with 1 proton separation at G of 0.137 MeV. So we look for interaction between the core and valence proton to reproduce this 1 proton separation energy. So for this interaction, we adopted an interaction from Svensson and Birch, which consists of central and spin orbit terms with Wood section geometry and Coulomb term. This potential reproduces the ground state energy for 8 boron with 1 proton separation energy, I would say. Then with same potential, the resonances are checked in complex scaling method. And it is found that, interestingly or surprisingly, I would say, with same potential, we have non-resonant continuum in other states, that is P3 half, S half, and other. But we have a 2-body resonance in P1 half continuum that can be seen in this figure on extreme right. So one can see the isolated resonance from the non-resonant continuum. And this 2-body resonance is obtained at energy 2.27 MeV above 0. But if we see it with respect to the 1 proton separation energy, then it is around 2.4 MeV with a width of 1.45 MeV. So now I would like to say that in the absence of core spin, which is 3/2 negative, so if it couples with the spin of valence proton, the possible coupling, the possible states are 0 plus, 1 plus, 2 plus, 3 plus. So due to the simplified model, all these states are degenerate with the ground state. So this, due to this simplicity, we cannot disentangle these states from our resonance state with by ignoring the spin of the core. But I would say this approximation is reasonable to proceed for 3-body calculations. Okay. Now, with this simple inert spinless core approximation, the ground state is represented by coupling the valence protons to 0 positive. And the continuum excited states corresponds to 0 plus, 1 negative, and 2 plus states. Now, the only free parameter in our framework is the strength of 3-body force in our Hamiltonian. So we tune this three-body force strength to reproduce the ground state, that is three-body threshold, as well as the first excited state. So as I explained, for three-body force, we make use of the product of Gaussian functions. And for 0 plus, we tune this parameter to reproduce the three-body threshold, that is 2 proton separation energy. Whereas for 2 plus, we tune this parameter to reproduce the energy of first excited state. Okay, what is in this table? So these are the results of the ground state and first excited state with different interactions. So when the three-body force is missing, the system is deeply bound. So in order to recover the 2 proton separation energy, we need repulsive three-body force. So by tuning that three-body force, we can obtain the correct 2 proton separation energy. Now one can ask me, why don't you use the same three-body force for all other excited states? I will come to it. Okay, so the first excited state is bound if I don't use three-body force, which is not the realistic case. So I can tune that three-body force to make all these 2 positive states unbound. But if I use the same three-body force, this state becomes weakly bound around O.3 MeV. Still, this is not the experimental situation. We further tune our three-body force strength to reproduce the first resonance at the experimental value, that is at O.781 MeV above the three-body threshold. So once we fix these parameters, now we are ready to explore the continuum of all these states which we have prepared. Okay. Now I will discuss the 0 plus continuum. Okay. So this is the complex energy plane where I have plotted the eigen energy values of the complex scaled Hamiltonian. So one can see these are for complex scaled angle theta equal to 20 degree. First thing. Then these are results for 0 plus state. On extreme left panel, when the three-body force is missing, means when we don't use three-body force, what happens? The ground state is more deeply bound. We have a three-body resonance at 4.1 MeV with this width. And these are this line is the two-body resonance. These are the two-body resonances because these are quite close to 4.2 MeV. So there are 3 two-body resonances which are the same 8 boron resonant state in P1 half. And another proton is sitting in non-resonant P1 half state to couple to 0 plus. Now, I would like to tune my three-body force, which is the only free parameter. So I tune it to some value which can reproduce the two proton separation energy. But what happens to the three body resonance when I tune this ground state or tune this accurate two proton separation energy? This resonance shifts to the higher energy, means it moves out of this picture somewhere in between 5 to 6 MeV. But these two body resonances remain unaffected. They are not affected by the three body force because these are the two body resonances. Now, let me make one general statement from these results. For 0+ state, the three body force optimizes the bound ground state. So basically, the bound states have more compact structure. So the three body force effect is visible on 0+ resonances, due to which this three body resonance is shifted to higher energy and it moves out of the plane or out of this picture. Moving to next continuum states, the 2+ continuum. Again, this is all these are for theta equal to 20 degree, but in this picture I have theta 15 degree and also 20 degree, just to be sure that if this is clear three body resonance. This is just a matter of choice. But when my three body force is missing, I have a bound excited state at 1.7 MeV and also a resonance at 1.4, three body resonance at 1.4 MeV, and these two body resonances are there, but these two body resonances in 2+ continuum are the one proton sitting in resonant p half state, but another proton is now sitting in either non-resonant p3 half or non-resonant f5 half state to couple to 2+. Whereas in previous case, this non-resonant component was in p1 half state to couple to 0+. Okay. Now, again, one can clearly ask me what will happen if I use this three body force strength the same as the ground state. Yes, this will move somewhere here. This will move somewhere here. But still I have bound excited state, which is not the realistic case. Then I further fine tune my three body force strength to fix the resonance at the known experimental energy. And with this choice of three body force strength, the higher lying or the second three body resonance moves to higher energy side. With this, we reproduce the first bound excited state. And again, here, the three body force strength is based on tuning the bound ground state, right? Bound state. The bound states have more compact structure, and due to which the effect of three body force is clearly visible. On changing from 0 to 5, this bound state becomes the narrow resonance, and this this resonance moves to the higher energy side. Moving ahead, interesting. Now, I would like to see the continuum of 1 negative states in 9 carbon. So here you can see the 3 panels. Again, in all panels, the complex scale angle is 20 degree. On moving from no three body force, means when three body force is 0, And this three body force is equal to the ground state three body force. And this three body force strength is equal to the one fixed for first excited state. So as if we see green circles, these are again two body resonances which are unaffected with the three body force, change in three body force strength. In one negative, now the one proton is sitting in the resonant p half state of 8 boron, and another proton is either sitting in non-resonant d3 half or s1 half to couple to one negative. Now we have three body resonances in one negative continuum which are unaffected with the inclusion of three body force. I would say weakly affected. To understand this weak effect, we think that it may be but it seems that resonances in one active states have extended structure. Of course, this is verbal statement. We need to see the density distribution, how I would say, the dineutron correlations for these states. That is separate story to claim this thing. But this is the impression, because we cannot see any effect of three body force on these resonances. So it seems that these resonances have extended structure. That's why they show weak dependence on three body depth. Whereas in case of previous 0 plus and 2 plus continuum, those three body forces are based on the tuning of the bound states, which have more compact structure. So that's why we can clearly see the effect of three body force or three body strength in 0 plus and 2 plus states. Okay, so this is the comparison of our structure calculations with the available experimental data. So this experimental data is adopted from this recent study, and I will come one by one. And this is the old data for this state, and this is the more recent data for another state around same energy. I will comment on these things. Our calculations with the spinless core approximation fairly reproduce the ground state as well as first excited state by tuning the three body force strength in our three body Hamiltonian. On top of that, with our simple approximation, our calculations suggest the three negative resonances, whose parity will be positive if we consider the spin parity of 7 beryllium. But interestingly, this recent reference, that one by Hooker et al., they have recently confirmed a positive parity state, that is 5/2 plus state around 2.863 MeV, around close to this level. So these states are still under discussion. And we believe with our efforts, a further investigation of these possible resonances states through a breakup cross-section will be interesting and important. Now, once we fix the structure of 9 carbon, we would like to see the role of these low-lying resonances in the breakup observables. So here I show the results of 4-body breakup of 9-carbon, which is achieved by making use of 4-body version of CDCC. We investigate the role of 0+, 1 negative, and 2+ resonant and non-resonant continuum states on the breakup cross-section. This figure shows the elastic breakup cross-section at 160 MeV, the 9-carbon breakup on lead target. If we concentrate on picture or figure or results, the shape of the breakup cross-section is guided by narrow peak around 0.781 MeV. In the lower energy region, less than 1 MeV, this peak originates from the narrow 2 positive resonance, and its contribution to the total breakup cross-section is around 32%. In the higher energy region, say above 2.5 MeV, the shape of total breakup cross-section is mainly determined by the 1 negative resonances or 1 negative resonance at above around 3 MeV, which I reported on previous slide. Thus, we find that 1 negative cross-section is dominated by the low-lying non-resonant continuum and high-lying 1 negative resonant states around 3 MeV. So in nutshell, 2+ appears as a 2+ low-lying resonance appears as a sharp peak in the breakup cross-section. The 3 1 negative resonance states contributes to the cross-section in higher breakup energy region of the energy spectrum as a bump structure around 3 MeV. Now, as a future work, it will be interesting if the breakup cross-section to the 8 boron plus p channel can be disentangled from this 3-body channel or 4-body channel, I would say. To this end or to achieve this aim or dream, we think that the practical p separation method that was discussed in last reaction seminar last week by Watanabe-san is expected to be helpful. But we still need to work on it if we need modifications, or we can use it directly. But this is the interesting direction to make use of that practical approach that was developed by Watanabe-san. So in summary, we reported first 3-body calculations of 9-carbon for its ground state and low-lying continuum states with the Gaussian expansion method combined with the complex scaling method. A 3-body low-lying resonance is found in 2+ continuum, whose position is fixed by adjusting the strength of 3-body force. The 3-body resonances in 1 negative continuum are obtained above 3 MeV. The breakup cross-section of 9-carbon on lead target at 160 MeV is performed via 4-body CDCC combined with complex scaling method. The 2+ resonance appears as low-lying sharp peak, and 1 negative appears as the peak around 3 MeV. As a future perspective, the future directions of this work are to explore how we can see or include the effects of spin-off core, other the most urgent need to implement is to disentangle the 8 boron plus proton channel breakup cross section from this 3-body channel breakup. Another interesting in the view of the recent upcoming experimental studies, which I reported in my motivation, because they are aiming to measure these removal cross sections. It would be interesting to implement these 3-body structure calculations to further investigate the 1 proton and 2 proton removal cross sections. And further, we can think of calculating evaluating or determining the astrophysical S factor. Thank you very much for your attention.